Welcome everybody to another of the Dig Deeper webinars. It's a great pleasure to be with you here today, and I have the joy of introducing the webinar today. The focus is on revegetating iron ore mine wastes. As always, I would like to start by acknowledging the traditional owners on the lands on which we meet, which for me here is the Yaga and Derbarl people. I'm based in Brisbane, and I'd like to pay my respects to elders past and present. I'd like to extend that respect to all the lands on which we meet across Australia, and CLC Time is located in multiple locations and we have a national profile. I really like to extend that respect across the great country. So it is a great joy to be introducing the webinar today. Thank you for joining us. I would like to point out that we are recording today, so let's let you know that we're recording, which means it will be available afterwards. We encourage you to share it with your friends and colleagues. It's a great format. And it's an excellent lineup today. I have the great pleasure of introducing the speakers. To start with, we're going to hear from Professor Hans Lambers, who is from the Netherlands, got his PhD in 1979, and has been professor at Utrecht University before migrating to Australia in the late 90s, where he's been a professor of plant ecology, plant biology and ecology at the University of Western Australia. So it's a huge pleasure to be inviting Professor Hans Lambers, and of course, also a great pleasure to be inviting Dr. Pallavi, who was born in India and did her PhD in the field of plant molecular and cell biology in Germany at the Karlsruhe University of Technology, Institute of Technology. She has been working at the International Rice Institute, so it's a lot of experience with the Rice Institute there, but currently, as with Hans, both Dr. Pallavi and Dr. Lambers are working with us at the University of Western Australia. So it's a great pleasure, and what I'm going to do is I'm going to hand over first now to Dr. Lambers, Professor Lambers, and then later on we're going to have questions. So I encourage you to put your questions in the chat. We'll hear from both speakers, and I will be then sharing the questions with the speakers, and we'll do some interactive at the conclusion of both of the talks. So over to you, Hans.
Thank you, Tom. Well, I'm going to report on our recent work, and the title of our project is Increase Bioavailable Plant Nutrients in Iron Ore Mineral Waste using a novel eco-engineering plant microbe system. The talk has actually been produced by my postdoc, Hong Tao Zhong, and I would have preferred him to present this talk, but he is back in China right now. He's still heavily involved in the project, and he could do that, but today he is not actually available. So I'm presenting this on his behalf. And I also would like to acknowledge the input of my colleague Erik Veneglaas, who is gradually taking over while I'll step back from this project. And like Tom, I would also like to acknowledge the traditional custodians across all the lands on which we live and work, and we pay our respects to elders both past and present. We do have problems. There's no other way to actually phrase that. If you look at the tailings, and I'm showing you two slides of those tailings, you can really see these are really problematic soils. They aren't even soils in the true meaning of the word. We have got vast quantities of mine tailings, and they tend to be very hostile and challenging to actually establish plants on them. But that also creates an opportunity, of course, because those mine tailings definitely have the potential to be turned into soil with the right approach of using plants and, of course, also microbes. And then you can work toward ecologically engineered soils, which can be effective plant growth substrates, but that of course requires some research how you can actually do that. So what Tao has produced so far is he has collected leaf and soil samples both at Christmas Creek and Cloudbreak mines. The soil samples have been analyzed for physical and chemical properties. We've analyzed the leaves as well for nutrients and also carbon isotope and nitrogen isotope composition. I'll tell you in a minute why we are very keen to look at those isotopes. And then the Glasshouse experiment was actually conducted using the alluvial waste that we transferred to Perth, and Tau used 18 plant species there. So we have 3 sites. One extreme is the natural reference sites, and ideally you would like to turn the tailings storage facility into something that looks like the natural reference sites. In between we have the rehab site, and you can really see there is a very steep gradient. Starting with the net reference sites, we need to collect information how that site actually functions to actually see what needs to be done to turn the tailings storage facility into something that looks something like the natural reference site. When we look at the pH, mostly the pH is fairly neutral, with the exception of the second bar here. That's a saline area. That's one of the reference sites, but that's a bit of an unusual site. For the rest, the pH is not really a challenging situation. It's fairly neutral. When it comes to electrical conductivity at the right, so you can see the electrical conductivity, which is an indicator for the amount of salt that is in the system. The reference site is not saline at all, but then the saline site, of course, is rather saline. And if you go to the other sites, the waste rock dam also has a pretty high level of salinity. So it's not a big issue, but at some sites it definitely is an issue we have to be aware of. Total carbon, or more importantly, organic carbon, because that is really what matters. It's not the carbonate that's really the organic carbon that is really of interest, because that's a substrate for bacteria, and those bacteria and other microbes, they are very important to actually build up the soil. So the reference sites has a very high organic carbon content compared to the rest. And at the airport rehab site, we also have a fairly high carbon concentration, but some of the other sites have, especially the vast tailings storage facility, has very low organic carbon concentration. So really, our efforts must be directed towards building up that carbon and turn the tailings into a functional soil over here. Nitrogen is a very similar story. Again, we need that nitrogen because that's a substrate for plants to grow on. And you can see that the vast tailings facility has very low nitrogen concentration. And that is an issue. So we really have to build that soil, and we need plants to do that. We need plants to do that either symbiotically with microbes, rhizobium, for example, or Frankia, depending on the species that we're looking at. So that can be done symbiotically. Of course, it can also be done non-symbiotically, but there again, we do need plants, because those non-symbiotic organisms that fix nitrogen, with the exception of cyanobacteria, they also need a carbon source, and that will have to be provided by a plant. So plants play an important role to build up the nitrogen in the soil. When it comes to phosphorus, we only have data here for total phosphorus, and not all that phosphorus may be available. And that is something that we really have to focus on. So total phosphorus, there is actually plenty of phosphorus, but to what extent that phosphorus is available is a different story, because phosphorus tends to be locked up in the soil, definitely when that soil contains a lot of oxides and hydroxides of iron and aluminium, and then plants cannot actually access that. Well, that is, most plants cannot access that, but we have a lot of plants in our vegetation belonging to the Proteaceae, for example, or belonging to the Cyperaceae, that can access that phosphorus that is strongly locked up in the soil. And they will have to play an important role to actually mobilize the unavailable phosphorus in the soil. That is a target in one of our Glasshouse experiments. We also looked at carbon isotope composition, at nitrogen isotope composition, and we don't need to worry about the details. What is important is to know that the carbon isotope composition will tell us something about the photosynthetic pathways that plants use, and they also tell us something about how efficient the plants use their water. The nitrogen isotopes will tell us whether those plants are actually fixing nitrogen. Symbiotically, we say Rhizobium or Bisfranchia. And they will also tell us whether the plants use inorganic nitrogen, such as nitrate and ammonium, or perhaps organic nitrogen, such as small peptides and amino acids. So if you look at the delta 15N values, you can see that the acacia value is close to 0. 0 means that the plants are totally dependent on nitrogen fixation. Well, this acacia is not 0, but is actually 0, a lot closer than this eucalyptus and this senna species over there. So what that tells us is that these acacia plants, they were likely dependent to at least some extent on nitrogen fixation to satisfy their demand for nitrogen. Whereas the other plants, not being legumes and not being capable of nitrogen fixation, they have a different isotope composition. And this isotope composition indicates that they likely access organic nitrogen. If you look at the carbon isotope composition, that will tell us these are all C3 plants. So not chem plants, which is typical for succulents. Well, we don't have any of that in this particular comparison. They're not C4 plants either. They are typical for tropical environments. Clearly, what we're dealing with here is only C3 plants. And these C3 plants, they differ a little bit in their efficiency of water use. The more negative value, the less efficient they are in terms of their water use. So that is the information that we get out of this carbon isotope composition data. Another side, again, the acacia has values close to 0. It must have been dependent heavily on nitrogen fixation. And of course, the other two species, not being legumes, not being associated with nitrogen fixing microorganisms, they had higher values. And it indicates that Tylotus and an organic N, and senna probably used a combination of organic and inorganic N. And when it comes to the carbon isotope composition, again, indicating that all these plants were C3 plants, there are no chem plants, that they are not succulent, they're not C4 plants either, and the acacia was pretty inefficient when it comes to its water use compared to the other two species shown in this graph over here. And again, going to another side, this acacia may have fixed some of its nitrogen, but given that it is not all that different from the other two species shown in the graph over here, it probably wasn't heavily dependent on nitrogen fixation for whatever reason. Maybe the right rhizobium wasn't there, nodulated. We would really need to dig up the plants to actually see whether they were nodulated at all. And then we could take action and say, well, if we want them to fix nitrogen, we may have to inoculate them with a rhizobium that forms a better association than what we have in this slide over here. And again, with the carbon values, carbon isotope composition, all C3 plants, and the acacia was the least efficient in terms of its water use. And another side, this acacia clearly was heavily dependent on nitrogen fixation. Its delta 15 value was close to 0. So it probably got most of its nitrogen from nitrogen fixation. That's really what we like to see. The other acacia, much less so. It had much more positive values. So it may not be fixing a great deal of nitrogen. And why that is, we don't really know that. We would need to dig up those plants and see whether they were actually nodulated. And maybe they weren't. If they were nodulated, they may not have been nodulated with the right rhizobium. So some action is possible there. And of course, the other two species were not dependent on nitrogen fixation. And again, carbon isotope composition, they're all C3 plants, and they differed a little bit in their efficiency of water use, but definitely all C3 plants. A Glasshouse experiment, Tao started one at the end of 2021 through for several months with a range of species. And he grew them either without rhizobia or with rhizobia. Now, with rhizobia, you might expect the legumes to do a little bit better. For the non-legumes, you would not expect any difference. What you see over here is quite a large variation, and it's definitely not true that all acacias, that all legumes grew better with the rhizobia than without the rhizobia. And it's also not true that the non-legumes were not affected by this inoculum. So these results are, well, a little bit all over the place and a little bit unexpected. You would not expect the non-legumes to respond at all, but they clearly did, which is a bit surprising. And this is the total biomass. And the next slide over here shows you the photosynthesis. And again, we see the same picture. The legumes with the rhizobia did not necessarily show a faster rate of photosynthesis than the ones without. And you see legumes which are not expected to respond at all. They definitely sometimes were affected. Now we still have to look at the significance of all these results, and we haven't quite got there yet. So in summary, pH is not much of an issue except at the saline site, but that was to be expected. And the same EC was not much of an issue except at the saline sites, but there is quite a bit of variation, so we really have to watch that and make sure that we have the right plants to actually grow at those sites where the electrical conductivity is somewhat higher than what you would expect, higher than at the reference site. The isotope composition, the nitrogen isotope composition, showed us that some legumes were definitely fixing nitrogen, but not all of them. And we still don't quite know why that was the case. Maybe they were nodulated, or they were not nodulated with the wrong strain of rhizobium, and that needs to be followed up. The carbon isotope composition showed us they were all C3 plants, and they varied a little bit in the water use efficiency, but there was not really an issue there. And several species in the Glasshouse trial actually showed potential for further testing in field conditions. And we also want to do further Glasshouse trials, but that's not included in this talk because I'll leave that to. So when it comes to applying the research that we have done so far, the work on carbon and nitrogen isotope composition can assist us in selection of potential N-fixing plant species. That is the nitrogen isotope composition, not the carbon isotope composition, of course. The carbon isotope composition tells us that anything over there is all C3 species, and there's no unexpected chem plants or C4 plants over there. But of course, we would really like to have legumes there that effectively fix nitrogen, because they have to bring in the nitrogen in the system, or Allocasuarinas can too, that's fine. But we can use the 15N isotope composition for guidance, which species actually are very effective at bringing in the nitrogen. And so listing potential pioneer plant species, including, of course, the N-fixing and also the P-mobilizing plant species, is really very important because, as I mentioned, we have data on the total amount of phosphorus, but a lot of that phosphorus is not available for plants that are not capable of mobilizing that phosphorus. Some plants, like Proteaceae, for example, will be very good at mobilizing that phosphorus. Some legumes may also be good at it, but that varies a lot. And we really need to do more work to actually find out which of these species are actually capable of accessing all that phosphorus that is in the tailings, because not all species are equally good at mobilizing that phosphorus. So next is to visit more mine sites, both for plant and for soil sampling, and actually try to the bottom of why some of these plants were fixing and others were not fixing nitrogen. And we also want to conduct more glasshouse experiments using mine tailings, but I leave that to Pallavi to talk about. And I basically acknowledge the input from both Kirsty and other partners at FMG to make all of this work. And rather than ask questions now, I think Tom indicated that he would prefer the questions to wait until Pallavi has also presented her talk.
So thanks so much, Hans. And yes, just as Hans said, we are waiting for the questions for after Dr. Pallavi. So I do see there's one coming in, but we will come back to that one after. And Pallavi, over to you. So maybe, Hans, if you can just stop sharing and Pallavi can start sharing.
Yeah. Done.
Good morning, everyone. I'm going to discuss about my ongoing research plan. So my first key objective is to investigate the use of soil ameliorants to improve in situ remediation for future restoration. As you already know that these tailings are waste material that is left after the target minerals are extracted from the ore, and they often possess extreme physiochemical properties such as high salinity, extreme pH, low content of microbial diversity and content. So we are going to use compost biosolid as a soil ameliorant, and I'm going to perform the glasshouse experiment to test the effectiveness of this compost biosolid in tailing remediation. I will discuss about this compost biosolid in the next slide. My second objective is to selection of pioneer legume and non-legume plant species and evaluating the effectiveness of nitrogen fixing bacterial strains. Although there are 98% nitrogen are present in the Earth's atmosphere, but plants are unable to take this atmospheric nitrogen directly because they are present in the form of inert diatoms. So this nitrogen fixing bacterial strains are extremely important. They are either free living or make a symbiotic association with plants, and they are capable of transforming this atmospheric nitrogen to the organic fixed nitrogen compound such as ammonia, which is consumable by the plant. So I'm going to test the effectiveness of isolated nitrogen fixing bacterial strain such as Bradyrhizobium arachidis strain to nodulate pioneer plant species. The reason why I have selected this Bradyrhizobium arachidis because although it is involved in the nodulation of the commercial crop, but it has been also reported that this Bradyrhizobium arachidis is capable to form nodules in the Australian native plant species. Before going to compost biosolid, I'm going to give a brief description about what biosolid is. So uh, biosolid is the product of wastewater treatment process. So during wastewater treatment process, this solid is separated from the liquid, and then this solid are treated physically and chemically to produce nutrient-rich compound called biosolid. Compost is further processed biosolid with lower pathogen concentration, and it has already undergone Department of Health for assessment. So it can be used as an unrestricted product and can be applied on large fields and other places where public contact is likely. They do not have any odor or a smell, and they contain low level of metal content in it. So that's why they do not have any negative impact on surface water or groundwater quality. They are sold as a soil fertilizer or soil conditioner. So compost biosolid is better or preferable over normal biosolid. This is the list of the species that I'm going to use in my glasshouse experiment. So these species are selected on the basis of the field visit to the mining site. So there are some species from Fabaceae family, some from Proteaceae, Chenobodiaceae, and then Amaranthacea. Now I'm going to discuss about my experimental design. So I will have control. Uh, First will be tailing, second tailing urea and biosolid, third will be tailing urea, and the fourth will be potting mix plus seed. So the reason why I'm using here potting mix is the because this potting mix will be the ideal condition of plant to grow. They are nutrient rich, and plants do not have any problem to grow in them. Seed here means the list of the species that I showed you on the previous slide. In the treatment condition, I have tailing urea biosolid and seed, and the second treatment will be tailing urea and seed. So the reason why I am using urea here, because I already mentioned in the previous slide, this tailing is deprived of, or they do not have detectable amount of nitrogen in it. So I'm going to use urea as a source of nitrogen in the tailing material. This biosolid will be served as nutrient rich media for the tailing. This experimental study will be carried out in 6 biological replicates, and the substrate moistures will be maintained at around 50% of the field capacity. I'm going to use this Bradyrhizobium arachidis to see if plants are capable to produce nodules or not. After the end of experiment, I'm going to do the sampling from the tailing materials, leaves from legumes and non-legumes plant, followed by lab analysis such as soil physical, chemical, and biological properties will be measured, and isotope of carbon, nitrogen, and other morphophysiological properties will be measured, including nutrient conditions. So now I'm discussing about the expected outcome. So from this experimental study, this will provide the valuable insights into the effect of compost biosolids on the restoration of future vegetations. Because our aim is to not only restore the vegetation, but to also induce the self-sustainable ecosystem in the mining sites. Second, we will be able to identify and select the native pioneer plant species in promoting effective ecosystem restoration. It will be helpful in establishing positive microbial activity and enhanced nitrogen concentration in plant. A significant outcome of this study is expected to improve nutrient availability in tailing plus composted biosolid mixture. In future, I'm going to visit more mining sites such as Western Hub, Solomon Hub, and then Iron Bridge, followed by the soil sampling, tailing samplings, and the leaf samplings, and then to do the nutrient analysis of the plant materials, and then soil physical, chemical, and biological properties will be measured. Laboratory and glasshouse experiments followed by experiments using a rain-out facility and field trials under mine site condition. Thank you, everyone.
Great. Thank you. Thank you so much. And thanks to both the speakers. So what we're going to do is we're just going to look at the questions that we have here. So there's already a couple of questions come through. First one is from Andrew Butler. Has the apparent salinity been characterized to determine what contribution is from chloride versus other salts? Someone want, Hans, I think that was addressed to you, Hans, because that came in while you were speaking.
We actually focused on the electrical conductivity, and of course that doesn't tell you which salts are involved, but we will also measure the total element composition of those tailings, and from that we should be able to tell whether it's actually sodium or any other compounds. At the moment I can't actually tell you whether it is just sodium and chloride or whether there are other element ions as well.
Okay. Right. So
it's not a big issue for most of the sites, so that's why we didn't actually prioritize that. It's only an issue where you see the salt scarce, but I mean that's not one of the key issues for restoration.
Sure. So what we might do then is move on to the next question. And this, Pallavi, you let me know if you want to add anything as we go question by question. I think this one, well, maybe this one's for both of you. It came in while you had started, Pallavi. So question is from Longbin Juan, and it says, has your team looked into pathogenic processes and indicators after growing the plants, as in our AR-CLP project with idle tailings? So soil structure development is critical, and in eco-engineered pathogenesis, fine detection and compacted tailings and spoils, which integrate interactions of microbes, mineral weathering, and so on. So do you have any comment on that question or comment there?
I'll start, but I'll then handball it to Pallavi, because I can simply say that in the first experiments, the growth of the plants was such that there was not much soil development yet. But I think with Pallavi's experiment, wonderful opportunity to measure all of that. And I think Pallavi can further comment on it and tell you what her plans are in that sense.
Yeah, so with the previous experiment performed by Tao, so he was simply used the tailing material. In my experiment, because I'm using other nutrient conditions as well, such as urea as a source of nitrogen, and then I'm also providing tailing with the this biosolid, composted biosolid as a source of other nutrient condition. So yeah, we will look like how the soil composition will be after the end of the experiment, after I will collect the soil samples, like the tailing samples, and then can analyze more about it.
Okay, There's a comment here or question here. Any thoughts on PFAS in the biosolids? That's fun. Seeing
I saw that question popping up, and I also saw that Nancy Bolan is in the audience. He may wish to comment on it. I would not expect that to be a serious problem, considering that we are dealing with municipal waste. And I mean, I know that PFAS is everywhere, and Nancy can talk more about that than I can. So I'm not saying that there cannot be any, but given that the source is actually municipal waste, I would not expect it to be a serious problem. But I would love to hear Nancy's take on this, because he knows far more about it than either Pallavi or I do. You're on mute, Tom.
Had to happen. So Nancy, if you just want to raise your hand when you're ready to comment on that, but just until we see that hand, we might just go to the next comment, which is consideration of the practical feasibility in scaling up eco-engineering inputs under field conditions. Do you have any comment about the practical aspects referring to scaling up in field conditions?
Well, that is something that we really have to discuss with people at FMG, because that's not something that we can actually propose. We need to do that. We need to develop plans in interaction with them, and of course, right from the start, we do interact with them, and we have outlined where we want to go, and of course, the ultimate outcome would be to apply what we are discovering in the Glasshouse, to apply that in field studies, and that is definitely the intention. And we want to develop those field studies on site, and we have plans for that, and we want to do that together with the people from FMG. But so we can't stop just with the Glasshouse experiments. We have to implement what we find, and that can only be done in Glasshouse. That can only be done in field studies, and they will be developed in collaboration with FMG.
Okay, look, that's very helpful. So there's a comment here from Thomas Baumgartel, which says water is the primary limiting factor for plant establishment and survival, above all in such artificial substrates like tailings or waste rock. Have you considered to include and measure this factor, and also in light of real on-site conditions? So I think the focus there is on the water as a limiting factor.
The field experiments would involve rainout shelters, for example. So we would include a water component there. But in our Glasshouse experiments, I mean, if we were to change the experiments that Pallavi outlined, and also include a water component, that would really double or triple the size of the experiments. So we want to take baby steps and first see what the nutrients actually do and what the plants actually do to the soil, and then we can worry about water aspects at a later stage. Because without the planting bringing in the nitrogen and the carbon, we wouldn't get anywhere. And I know that bringing in the nitrogen and the carbon will be affected by water, but let's first see which plants are really very good or very bad at bringing in the nitrogen and the carbon, and then we can impose a water treatment.
Pallavi, did you want to add to that or comment?
Yeah, so yeah, we are just doing this Glasshouse experiment first because we want to be sure if this biosolid and urea is actually contributing this tailing material and support plant to grow better. And then once we succeed in this, we can implement this on the field area. So yeah, that's why we are doing the Glasshouse experiment first, because then we can provide the control conditions to the plant, and then we can proceed to the larger area. So this is the idea.
That's great. So we do have time for some more questions. If anyone would like to raise their hand or comment on any of the discussion up until now. So we have option to put in the question or comment via the chat, or also we can also take some live. What I was going to ask myself, just in case as people wanted a moment to think about that and add their comments and questions, what I'm quite interested in is from your experience, where have you seen the really interesting and successful examples of this sort of work overseas? So what have you seen some, I mean, obviously you've worked in a range of different contexts and you've seen this sort of work before. I'm quite interested in what you've seen from other situations in other contexts. Is there some sort of thoughts you have about that?
I'm not entirely sure I fully understand your question.
Similar work overseas. What are the interesting lessons and insights?
I think the approach that we are very keen on taking is using plants that bring in the carbon and bring in the nitrogen. And we have a unique opportunity to select plants that are very good at bringing in the carbon, because and they do that because they use that carbon to actually access the phosphorus in the substrates. So they improve the situation in both ways, in two ways. They make the phosphorus available, which is important, but by doing that, they also bring in a lot of carbon with their carboxylate releasing cluster roots, for example. So that's why we are very keen to include a grevillea, an endemic grevillea and an endemic hakea in the Glasshouse studies. And I think that's an approach that we are taking that most other people have basically ignored because they understand much less about that component of our vegetation.
And yeah, and also I would like to include that Tao already found that there is one species from Mariana. Despite there is in the tailing area there is no nitrogen content in the tailing material, but this plant is able to survive and able to grow. They adapted like high transpiration rate, so they scavenge whatever nitrogen is present there, and so that they are able to survive there. So this is also a like good report, and we can use this species to test the further potential in the other tailing areas.
Longbin is making a comment I see on the chat. He says there won't be many biosolids on site. That is true, but FMG is not worried about that because we don't use biosolids, we use pelletized material. And Pallavi explained that very well in her talk. And that pelletized material is very easy to transport. So the idea is not to use raw material, raw biosolids that are generated on site. The idea is to actually use the material that is produced in Perth and can readily be transported.
Yeah, so we are using not biosolid, but the composted biosolid, because when we are using the biosolid, we need to take the license, and then there is a health issue and safety issue. Plus, they have a lot of moisture content in it, so the transportation will be the problem. So we are using the composted biosolid, which is treated like chemically, and they have lower pathogen concentration in it, and they are very safe. We can transport them because they are lighter in weight. They are in the form of granules or in the form of powder. So yeah, we are using the composted biosolid despite of using the biosolid.
Okay, great. Looks like there's a comment here. I may have missed it. Apologies. So what sort of nitrogen concentration can be achieved in the pelletized biosolids?
But there's very little nitrogen in biosolids, so that's why we have a treatment where we also add nitrogen in the form of urea. I mean, the biosolids contain lots of nutrients, but most of the nitrogen disappears. So we don't rely on biosolids as a major source of nitrogen. We would need to add that as fertilizer, inorganic fertilizer, artificial fertilizer.
I just wanted to go back to one element of an earlier question where we talked about the water, but part was also a question around the different types of waste materials. So are you looking at the multiple types of materials? So not just the tailings, but also the rock and wastes and so on and so forth. You've been looking at more than one types of material, or do you plan to?
First experiment, we just focus on the tailings that are provided by FMG, and that is their priority to have a look at those tailings. At a later stage, we may wish to consider looking at other material as well, but that will all be done in consultation with the industry partner.
Yeah. Yeah.
So I won't exclude it, but there's only so many hours in a day. And although Pallavi works very hard to actually double the experiment by looking at different materials or triple the experiment, that's not an option right now. But it's not excluded for the future.
Possible follow-up piece of work. Okay, so it looks like there's just another question coming in, and we still have time for a couple more questions if people would like to still have some. We still have a little bit of time. So the question here from Michelle Gardner: are you planning on also consulting with the traditional owners before you do trials on site? These FMG sites are extremely close to significant environmental and cultural receptors.
I think that's an excellent question, and that is definitely something that we will have to explore. And again, we'll have to explore that in consultation with FMG, because it's their sites, and of course, no action will be taken unless we've got all the permits that we need, permits from DBCA, but the traditional owners are just as important as DBCA, of course. So I think it's a very good question, and we will definitely take that on board and plan everything in consultation with FMG and make sure that all the permits and all the consultation will be there before we do anything on the ground.
Okay, no, look, that's been great. And what I also see in the chat for everyone who's on the call, on the webinar, Ben has posted some information about the projects. So they have some links there to look at these projects. And of course, while you're there, you can look at all of our projects or some of the other related projects, interesting projects that are being done by CLC Time. So we do encourage you to have a look at these reports and these project descriptions and so on. And then what we probably might do now is wrap up the webinar. If you have like to say any closing thoughts, Pallavi or Hans, you're very welcome to add those now. Would you like to make any sort of closing comments?
If people have further questions and they think about them after we close this session, then they should feel free to either email Pallavi or me or Tau or all of us and Erik Veneglaas as well, and we will be delighted to answer further questions via email.
Excellent. So Ben has posted there that we do have the next Dig Deeper webinar coming up, future-proofing a small local government authority against the impacts of the mining boom and bust cycle. So please do have a look at that for the next Dig Deeper webinar. It's a really excellent series where we get to engage with fabulous researchers and discuss the big issues here at CLC Time. So on that note, I'm going to thank you, both the speakers. Thank you, Pallavi. Thank you, Hans. And thanks to everyone who's dialed in, and also for the discussion and some debate, which is always healthy. We encourage debate, so thank you. And we're going to close it there, and we'll see you at the next Dig Deeper webinar.
My pleasure. Thank you.
Thank you.
Thanks, everyone.
Thank you so much. Yeah.